Hey, what's up, guys? This is chapter 4, beginning of chapter 4, chemical bonding. So a lot about chemical bonding is within the molecule itself, and then within outside the molecule. So how the molecules interact with each other, and what's inside the molecule itself. So mostly a continuation of chapter 3. All right, so types of chemical bonds. We should be familiar with all the type of bonds. You have the bonds that are between the atoms, so how atoms are interacting. Okay, and then we also have ionic, that's the transfer of electrons. We have covalent, which is the sharing of electrons. Metallic, which is the sea of electrons, so electrons are within like exactly what it is, a sea. Okay, then we have the forces between the molecules. So there are two molecules and then how they interact between each other. And that's intermolecular forces. We have van der Waals forces. Okay, those are basically temporary interaction between the forces. We have permanent dipole-dipole. We have hydrogen bonds, and we have electrostatic force or ion-ion bond, which is the ionic bonds or ion compounds. So we have chemical bonds: ionic, covalent, metallic. Within each of these are intermolecular forces. So for ionic bonds, they have an ion-ion force. Very strong, produces high boiling points, high melting points. And within covalent bonding, you have nonpolar substances, which are going to be your van der Waals forces. Okay, these are very weak intermolecular forces. So these are your typical gases like chlorine gas, fluorine, nitrogen, oxygen gas, methane gas. Very weak. That's why they're gases at room temperature. Then you have polar substances, and this is broken down into two types. You have your dipole-dipole forces. So these are your polar substances that are mostly liquid at room temperature. And then within that, you have hydrogen bonding, which is only a bond between H and O, H and N, and HF. So water, hydrofluoric acid, and ammonia, NH3, are your common hydrogen bonding. So these are like dipole-dipole, but stronger than your dipole-dipole. And then you have metallic, which is there's no force between metallic compounds because there's no compound. It's a atom or element. Zinc, copper. Okay, so there's no force in metallic bonding. All right, so that was a quick overview. So ionic bonding, very common, very easy. It's the complete transfer of an electron. So for example, sodium is going to take its outer electron, going to give it to chlorine. So now chlorine has a full outer ring of 8, and sodium lost its outer ring, so it has 8 because now it goes from the third energy level to the second energy level. So this goes back to electron configurations, losing its shell to become a noble gas configuration. Now sodium loses an electron, so it becomes +1, a cation, where chlorine will gain 1 electron and become an anion. Ions are produced, metals lose, nonmetals gain, and charge depends on how many electrons they gain or lose. And then the bond forms are between the positive and negative attractive force, electrostatic force. They form crystals. That's why you have like salt crystals. Ions form a repeating pattern, and very strong bond. Takes a lot of energy to break. Ion-ion force, the same attractive force between the actual ions and within the structure itself, because a sodium ion is going to be attracted to chlorine ions, and since they're in a regular pattern, they're right next to each other. So this is the intermolecular force, an ion-ion force. Dot cross is a very common way to represent these. Basically, you just show the outer ring, or the rings of the Bohr model of the element, and you show that sodium in this case is a +1 because it lost its 1 electron, and chlorine you see has an extra electron, and their configurations are 2,8, and for chlorine 2,8,8. Show the outer electrons. So for sodium, there's no electrons left over, and the outer ring goes from a third energy level with 1 electron to 0, and then chlorine will gain that 1 electron and has a full outer ring. This is more of a simpler method than writing all those inner rings with chlorine and sodium. So you just show empty sodium, and then you show a full chlorine with an X or a cross representing the lone electron from sodium. So use brackets, and notice the full outer shell in chlorine and the empty shell in sodium, and then you put the charge in the upper right hand corner. Alright, here's an example of calcium chloride. So you notice calcium, has 2 outer electrons, so it's going to give 2 away. But chlorine only needs 1, so you got to bring an extra chlorine in there to get the other electron from calcium. So that's why the formula for calcium chloride is CaCl2. So calcium has 2 valence electrons, chlorine need 2 chlorines to accept 1 electron each, so therefore the formula is calcium chloride. Or, sorry, CaCl2, because it needs 2 chlorines for every 1 calcium. Alright, magnesium oxide. So magnesium oxide is MgO. The reason why it's MgO is because magnesium has 2 outer electrons, just like calcium. Oxygen has 6 outer electrons, so it needs 2 more. So it's going to, magnesium is fully going to take its 2 and then give oxygen the 2 from magnesium. It's basically like a fair swap, 1 and 1. So that's why the formula is MgO. So 2 valence electrons for magnesium. Oxygen has 6, so it needs 2 more to get to 8. Therefore, we call this a 1-to-1 ratio, because 1 magnesium will transfer 2 electrons to 1 oxygen to gain 2 electrons. Alright, so this is your first homework for chapter 4. You're going to do dot cross of potassium chloride, sodium oxide, calcium oxide, and magnesium oxide. So there's 2 ways you can do this. You can do it on a piece of paper and then upload the picture to Teams, or I'll put them on OneNote, and then you can draw it yourself on OneNote as well using a touchscreen. So either way will work. All right, covalent bonds. So covalent bonds are the sharing electrons. So the key thing with covalent is that they have to give you the 8 electrons around the ring. Okay, so chlorine has 7 valence electrons. These are always going to be between nonmetals. They're going to share electrons to give you 8. So in chlorine is sharing 2 electrons to make a bond right here. They have 7, and chlorine has 7, so when they share 1 each, it gives you 8 around chlorine. Okay, so that's how you count, is that these electrons here in the middle between chlorine are going to be sharing between the 2. So to count chlorine on the right side, you have 7 or 6, 7, 8, and then chlorine on the left side has 6, and then 2 in the middle gives you 8. Lone pairs are not included in bonding. So you can see it has the red X's are lone pairs, and the only bond is between one X and one square, or dot. So how you draw a covalent dot cross is you have in dot and X's or crosses for the other symbol. You draw the outer electrons in pairs to emphasize the bond pairs and the lone pairs. And then the most molecules follow the octet rule. There are some exceptions, and we will go over those as well. So here with hydrogen, hydrogen breaks the octet rule because it can only hold 2 electrons. So it's going to make one bond with no lone pairs. So you can see it's just a one bond between H. There's no lone pairs around hydrogen. Okay. So again, why isn't there 8? Because hydrogen can only hold 2 electrons. All right, here we have methane, CH4. So how many electrons does carbon have? Valence is 4. So we draw 4 dots around carbon. Okay, so how many does it need? It needs 4 more to get to 8. So we take the hydrogen. Hydrogen has an X. It's going to transfer over, not transfer, it's going to share over and make a bond. So now it has, carbon is now having 2 electrons here with hydrogen. It's going to repeat itself to give you 4 H's. So again, notice it has now 8 electrons around carbon, 2 around hydrogen, because hydrogen can only hold 2. Okay, and so those are covalent bonds. So to draw a structural formula, we just change the electrons to like lines to represent a bond, and then you have the formula for the structural formula for methane, CH4. So now carbon has 8 outer electrons, hydrogen has 2, so it's happy. Here's water, H2O. So notice oxygen has 6 valence electrons, so there's 2 already pairs. That means there's only 2 spots where hydrogen can go and bond. Okay, so that means hydrogen can come in at the left side and the bottom, and then you have the bond between the sharing electrons, a covalent bond here, covalent bond on this H, and then you have the structural formula showing 2 lone pairs of oxygen. Here is ammonia. Nitrogen has 5 valence electrons, so it has already 1 pair. So that means it needs 3 more to get to 8. So notice it has 5 plus 3 gives you 8. So the formula for ammonia is NH3 because it needs 3 hydrogens to come in and share its electron to form a covalent bond at each of the open electrons. So it's 3 bonds, covalent bonds with hydrogen. Hydrogen chloride. Chlorine has 7 valence electrons, so it needs 1 more to get to 8. So the formula for hydrogen chloride is just HCl because it only has 1 spot where hydrogen can come in and share. All right, so here are some exceptions breaking the octet rule. Boron is one. It can be electron deficient, can hold 6 electrons. It's happy to be 6. Sulfur can expand the octet rule, and so can phosphorus, to 12 electrons for sulfur. Here's boron. Here's boron trifluoride. It doesn't matter if it's fluoride or hydride. It's still only going to share 1 electron. So boron here is going to only have 3 open spots. It doesn't need a pair here because it can be deficient. And fluorine can come in at 3 of the spots, share its electron, make a bond, and the formula for boron trifluoride is BF3. Sulfur has 6 valence electrons, so since it can be an electron expander, it can have 6 bonding sites. So in this case, sulfur hexafluoride, which you gotta say like deep voice sulfur hexafluoride because it changes your voice to Darth Vader. Like helium makes it helium makes your voice squeak, where sulfur hexafluoride makes it deep. So it can fit, since it can be expanded, it has 6 bonding sites. So that means you can fit 6 fluorines to make sulfur hexafluoride. All right, homework question number 2. Again, you can draw these and upload a picture to Teams, or you can draw them on OneNote as well. So this is tetrachloromethane. Tetra means 4. Okay. Phosphorus trichloride. So trichloride means 3 chlorines. And then a bromine molecule. Remember, bromine is diatomic. All right. Showing double bonds takes a little more elaborate work. So oxygen has 6 valence electrons. So we put 6 here. Okay. And it's O2. Again, 6 valence electrons. All right, so you can see you can form a covalent bond like that. Okay, 1 to 1, perfect. But if you count the electrons around oxygen, there's only 7. 2, 3, 4, 5, 6, 7, and 7 on the other one. So you should notice that oxygen here on both ends has a lone electron, which is not good. It needs to pair up. So what happens is they are going to 7 on each side, they're going to share because they don't make the octet rule. They're not met. Okay, so more sharing is required, but from where? And that's where you get these electrons on the outer ends to come in and make a bond. So now you have 4 electrons bonding in the between oxygen atoms. So 4 electrons means you have 2 bonds. So it forms a double bond between oxygen. They both have 8 electrons now on the around oxygen, 4 in the middle, and then 4 on each outside. So to make more bonds, you have to bring in more electrons to share. Here's carbon dioxide. So notice carbon has 4 valence electrons. So it needs 4 more to bond to make the octet rule. So it's going to form 2 oxygen atoms. Each lone electron is going to form with 2 carbons. So you need 2 of these oxygens to share on both sides of carbon. That's why the formula for carbon dioxide is CO2. Here we have ethene. So same idea in ethene. Ethene has carbon as a central atom. It's going to share 2 electrons with hydrogen each. Okay, so that forms the single bonds with hydrogen and carbon, but that leaves the center deficient. So that's why the extra electrons in the carbon have to form and share to make a double bond. Triple bonds, same idea. Nitrogen, notice nitrogen has 3 open bonds because it has 5 outer electrons. So it's missing 3. And nitrogen has 3 over here, has 3 over here, so they can form and make a triple bond. Here, here, and here. Alright, coordinate bonds. These are paired electrons from one element. So if you look at ammonium, NH4+, the hydrogens are bonded with sharing with 1 hydrogen, 1 electron from nitrogen and hydrogen. So that's formed a covalent bond. But if you notice this hydrogen here right here, it has 2 dots. So the dots came from nitrogen itself. Hydrogen didn't share any electrons here. So that's called a coordinate bond, or coordinate bond. Okay, so that's kind of tricky. Sometimes you'll see that question in a ACE, a multiple choice question about coordinate bonds. So again, showing coordinate bond here in aluminum chloride. So this aluminum chloride is one of the kind of exceptions that forms a covalent bond because of the coordinate bond here between chlorine and aluminum. So notice chlorine here is sharing both of the electrons with aluminum to form a coordinate bond. Here and here. Alright, we're going to do some practice on checkup number 4. So you want to practice showing the coordinate bonds between boron trifluoride, BF3, and ammonia, NH3, and it's going to form a bond between our compound F3BNSH3. And then phosphine, and PH3 and hydrogen ion are going to form the ion PH4+1. Okay, so you want to practice that and pause. Alright, so BF3 has a bond with fluorine. Okay, and NH3 has 3 hydrogens with a lone pair. Okay, it's not very clear. Pair, pair. All right, so here is that coordinate bond, and that's going to come in and make a bond with bromine. Okay, so I'm clear. Okay, so we're going to show the coordinate bond right here. Okay, and there's a boron, and then we're going to show hydrogen and fluorine, like so. So this is the coordinate bond between boron and fluorine. Okay, so it's clear that alright, so for phosphine has 5 valence electrons, and you see it's bonded with hydrogen. Okay, so you can see here, that's where the coordinate bond is going to be. H is going to come in, and you show that they are the same bond, or same electrons from phosphorus with 2 dots. If it was like a dot cross on here, there wouldn't be a coordinate bond. The coordinate bond has to be the same shape, so both X's or both dots. Alright, bond energy. So what happens with double and single bonds? So notice that the single bond is a lot less energy to break, almost double between a double and single bond. And you can notice the length also shrinks. So the length of a double bond carbon is at 0.134 nanometers, and a single bond 0.154 nanometers, which makes sense. There's more electrons, so there's going to be a more energy to break, and then it's going to have a tighter bond length. So bond energy equals the energy needed to break 1 mole of that given bond in the gaseous molecule. Again, if we want to break something, like take an electron away, it needs to be in the gaseous phase, and it measures the strength of the bond. Okay. So, showing double integral bonds, here's a structural formula. Each line represents a pair. So you can see the single bond has 1 line, double bonds have 2 lines, integral bond has 3 lines. As triple bonds, they're the strongest ones, so they have the strongest traction, they're closer together, they require more energy to break. Reactivity is influenced by bond strength. Notice that hydrogen is more reactive than oxygen, and oxygen is more reactive than nitrogen. That's because of the amount of energy to break. Polarity also influences reactivity. Neither of these are polar molecules, and we'll talk about polarity later. Reaction occurs when more collisions. Reaction occurs when collisions of molecules breaks the bonds. So again, if it's easier to break the bonds, it's less collisions are required. It's going to faster react. All right, checkup number 5. This is on page 56. Notice the bond lengths of HCl, HBr, HI, and how much energy is required. So again, the shorter the bond length, the more energy is required to break the bond. So what's the relationship between bond length and bond energy? We see this bond length increases, bond energy decreases. Why does energy decrease? The size of the halogen increases, therefore the bond and electrons are further from the nucleus, creating a weaker attraction. Creating a weaker distraction, not weather distraction, type error. And then suggest the value of what the length in HF would be. So notice the trend, HF is on top, so we should see that the bond length is going to be less than 0.127, probably close to 0.100. Notice the trend is about 0.02 difference between each one. All right, a lot of information here. If you have any questions, let me know, and work on those 2 homework assignments within the middle of the presentation.